This is Fluent Project 2. I'm Maddox Gonzalez. I'm in a team with Gabriel Spina. And to start off this project, we have fluid flow over a flat plate. We go in Workbench on Ansys, load up geometry, and we can start a sketch of our flat plate. So start by going normal to the XY plane, and we can just click up here and click on sketch. We draw a rectangle, we apply, and then if you highlight each side, you can click on generate, and then it will generate your solid plate. And then by left control and left click, you can click on each side again to name each side. So I named my left plate or left wall inlet, my right wall is my outlet, the bottom wall is the flat plate, and then I named my top wall as my symmetry for for meshing. So that's it in Sketch. We don't have multiple sketches this time. So we can close out of that and go to meshing. So I started with meshing. You see everything is more detailed towards the bottom because we're using everything is in reference to the flat plate bottom. So we want more processing power to be focused on the results on the bottom, which we're interested in. The top has bigger squares, so we're not as interested in this part. So to insert meshing, we would right click on insert here and we would click sizing and then we would apply it to the area of the plate and then we can list how many divisions we want each, or rather the area of the plate we list it to each side. So I started with the inlet and I put number of divisions. I think I put around like maybe 100, and then I put more towards the bottom. I didn't have many towards the top because I don't want to waste processing power when we're not interested in the results at the top. I already have my meshes here. This was my first one. I did the inlet and I did the outlet. Yeah, so here, number of divisions, I have 100. So my second sizing was for the top wall and the bottom wall. Here I have 200. And then the last one was on the entire face that I applied to the face of the flat plate. I cut it up into quadrilaterals and I applied that, and then it gave me a nice mesh at the end. We know everything is good because we don't have any yellow. So yellow is field mesh. So that means it's not actually processing. And we can, once we finish that, we close out of meshing, we can move on to results or setup. So same thing as project one, double precision on. I have four processors. So we do it. All right, so our mesh gets imported into here properly. We know we labeled everything. We know we labeled everything in the sketch and mesh settings because it correctly identifies that these blue lines are pointing inside the sketch, which says that this is our inlet. These red lines are pointing out of it, so that's our outlet. So we know we did that part right. Our meshing seems to have loaded pretty well, and we have exactly what we wanted. We don't have much detail in the top. We have everything down here in the bottom, the flat plate, which is where we're measuring anyways. So first thing we want to do, we open up our model, and we want to make sure all of this is turned off and viscous is set to laminar. So that seems checks out. So once we're done with that, we can go to materials. We open up our fluid. So we change, according to the rubric, we change our density to 1.2 and we change our viscosity. We just rounded up to 1.8. So we just fix that, change and create, close this page. So we're done with that. We don't need anything in this one. Now we just get to boundary conditions. So also according to the rubric, the free stream velocity was specified to 2 meters a second. So we open up our inlet, we go to velocity magnitude, make sure reference frame is absolute, and you have set this to 2. So apply that, close. Next, we want to set our outlet to pressure outlet. I believe it sets that as default. Same thing with symmetry. This is the top wall. I don't change anything here. I just leave that as default. And then I just want to check for my flat plate bottom that the wall motion is set to stationary. We don't want it moving. And we also have it as no slip for the shear condition. And then once we set that, all we're really changing is just the inlet. We want to change the free stream velocity to. Once we do that, we can close out of boundary conditions and we can go and run our calculation. So right click on run calculation, initialize and calculate. So also on the setup tab is where we can pull up our skin friction coefficient plot. We go down here, we open up our drop down for plots. We click on XY plot. And now we have this page. So I'm going to name my plot skin friction coefficient. So our y-axis is going to be wall flux and we want skin friction coefficient. So change that. Our x is against positions in meters. And we want it in reference to the flat plate surface. Then we can open up our axes and we can change the format. So I put float and do double precision. And then for Y, float, double precision again. And then save plot. And then it pulls up here. So this is skin friction coefficient. And then, so to find our drag coefficient, we can open the dropdown in solution manual. I already have it here, but so we open up our report definitions. I'm going to create a new definition. I want a force report and we're looking for drag. So we're going to click drag, have drag coefficient bubbled in. And then this is to the flat plate on the bottom. I want to print this result to the console. We press compute and then we press OK. We can close all this. And this is our drag coefficient. And then we have everything we need here. So we got our residuals. We have our skin friction coefficient plot here. And we have our drag coefficient computed from Fluent. So now we can close out of setup. Go back to our workbench and open up results. So this is the results tab. To begin, we want to add a contour. So the rubric asks for pressure contour. So I'm going to go ahead and add a pressure contour. I'm going to have 100 contours. We want it to be to symmetry 1. So we're going to set that as the location as a reference. Um, this is all fine. We can go ahead and apply that. And this is the pressure contour. So zoom in into our bottom. And this is part 1 right here. So now to add velocity vectors. So on the top here, there's a vector tab. We can click on that and we just name this velocity vector. So velocity vector. And we can set our location. So we're going to set our location as symmetry 1 again. And then we can change our symbol. I use this one. And up the size a bit of our arrows. And we just go ahead and put that. That is, let's change our arrow. Let's change the size. Getting closer. Let's try 0.05. Yeah, that looks a bit better. Um, these are good. So this is our pressure contour with velocity vectors added. Oops. So makes sense so far. This is pretty good. And next, so now that we have our pressure contours and we have our velocity vectors, the last two things we need is our plots. So we need our plot for wall shear and velocity profiles. So if we click up here, we can click on chart and make a new chart called velocity profiles. I already have my charts video over here. So change the title to velocity profile and go to data series, and we're going to have to import 2 locations, or we just select 2 locations. So in this case, we have our 35 centimeter spot and our 75 centimeter spot. So those are our 2 functions. Our x, we set our variable to velocity. We do the same thing for y. And that is it for our velocity profile. Next was wall shear. And I have my wall shear open right here. So we did the same exact thing. So this line is at the flat plate, which is why we had to add that in the first place. So we could set that as a reference point to plot our wall shear stress. Our x-axis we just have as x, our distance, and we set the variable for y as the wall shear force. And then that's it. Then we can plot it and take our screenshots and then submit. And we're done.